Welcome to Educator.com. Today we're going to be working on techniques for multi-step inequalities. So what we're going to be doing is putting together the techniques learned previously to solve inequalities that are a bit more complex. So there's a similarity between multi-step inequalities and multi-step equations. We solve a multi-step inequality using the same techniques that we use for solving multi-step equations. Remembering, of course, the big difference that if you have to multiply or divide both sides of the inequality by a negative number, you must reverse the inequality symbol to ensure that the solution set of that inequality is the same as the original inequality. So if I look at an inequality such as 3x plus 5 is greater than negative 6. In order to solve that, I do need to take a couple of steps. I am going to need to subtract to move my 5 over to the right side, and I'm also going to need to divide in order to isolate the x. I'm going to need to divide both sides by 3. So this is where I need to take multiple steps in order to solve the inequality. Sometimes you will see that an inequality contains a grouping symbol, and in that situation you use the distributive property to eliminate the grouping symbols, such as parentheses. For example, I may be given an inequality such as 3 times x plus 5 is greater than 2x plus 7. So I have x plus 5 in parentheses, and just as we have done previously with equations, what I'm going to do is use the distributive property to multiply out this term out here by each of the terms in the parentheses. So my first step in solving this is going to be to multiply 3 times x plus 3 times 5, which is 15. That actually should be 2x plus 7. 2x plus 7 on the right. Okay, so my first step in solving this inequality was to eliminate the parentheses through using the distributive property. Once I get to here, then I can go ahead and use my techniques of addition, subtraction, multiplication, and division to isolate the variable on one side and find the solution set for the inequality. Okay. There are a couple of special cases with inequalities. If the solution set of an inequality is an inequality that is always true, the solution set is the set of all real numbers. For example, I may have an inequality, so in this first case, I may have an inequality such as 2x plus 1 is less than 2x plus 5. So what I'm going to do is subtract 2x from both sides because I want to get my variables all together, and then what you're going to see is what happens right now is that since I'm subtracting 2x from both sides and there was a 2x on both sides, the variables drop out. 2x minus 2x, that's gone. So I'm left with 1 is less than 2x minus 2x. That one's gone. So I end up with 1 is less than 5. Well, 1 is less than 5. That is always true. So the solution set for this inequality is all real numbers. Okay, another special case can occur. If the solution is an inequality that is never true, the solution set is the empty set. Let's look at a situation where let's talk about a situation where the variables dropped out, like this, but then I end up with something that is never true. So if I had a situation like 2x plus 8 is less than 2x plus 5. Look at what happens. I subtract 2x from both sides. Variables drop out. Okay, my x's drop out. I end up with 8 is less than, my variables drop out, 8 is less than 5. Well, it is never true that 8 is less than 5. So what I'm going to say is that the solution set is the empty set. And you can write it as this empty set of braces. You can also write it like this. That indicates the empty set. So two special cases. The first one is an inequality that is always true, and the solution set is a set of all real numbers. The second situation is an inequality that is never true. So this is always true. So all real numbers are the solution set. No matter what number I make x, this inequality will hold up. Okay, so then I look over here and I have the opposite. I have a situation with an inequality that is never true. So the solution set would be the empty set. Most of the time, though, we're going to see a typical solution set, not all real numbers or the empty set. What we're going to be working with is mostly, but not always, a typical solution set. So in this first example, again, this is multi-step inequality, so it's going to take us more than one step to get this taken care of. I have 4x plus 24 is greater than or equal to negative 32. My first step is going to be to subtract 24 from both sides. That'll give me a 4x on the left and a negative 56 on the right. My second step is going to be to divide both sides by 4. Now, whenever I'm multiplying or dividing, I just stop and double check and say, okay, I'm dividing by a positive, so I'm okay. I don't need to reverse the inequality. I can just proceed. So I have my 4's canceling out, which gives me x is greater than or equal to negative 14. I'm writing my solutions as inequalities. However, remember, you can also graph the solutions. You can also write them as using set notation. So this took two steps. It first took subtraction of 24 and then division by 4. In my second example, I have negative 8y minus 12 is less than 20. My first step is going to be add 12 to both sides. And that's going to give me negative 8y is less than 32. Now, my next step is to divide both sides by negative 8. This is a negative number. So I also have to, at the same time, reverse the inequality symbol. Because if I don't, I won't get the correct solution set. So I have negative 8y divided by negative 8. So I'm going to immediately reverse this. This was less than. Now it's greater than. 32 divided by negative 8. Okay, so what I end up with is my negative 8's canceling out, so I get y is greater than negative 4. Okay, just to review, my first step was to add 12 to both sides so that I ended up with a negative 8y is less than 32. In order to isolate the y, I had to divide both sides by negative 8, and as soon as I saw I was dividing by a negative number, I went ahead and reversed the inequality symbol, which gave me a greater than. So I ended up with y is greater than negative 4. Again, I could represent this on the number line. And it's telling me that y is greater than. Not greater than or equal to, just greater than. So I'm going to use an open circle. And everything that is greater than that value of negative 4 is part of the solution set. In my third example, I have a negative 2 times z minus 4. So I have some parentheses. I'm going to have to take care of those before I go any farther. Okay, so minus 7 is less than or equal to 3z minus 6. So my first step is going to be to remove the parentheses. After that, then I'm going to proceed as usual. Rewriting this. Okay, distributive property. I'm going to multiply each element, each term inside the parentheses by negative 2. So that's going to give me negative 2z, and then negative 2 times negative 4 is plus 8. And then I rewrite the rest. Minus 7 is less than or equal to 3z minus 6. To simplify this a bit more, what I'm going to do is combine like terms. So I'll get negative 2z, 8 minus 7 is 1, plus 1 is less than or equal to 3z minus 6. I want to move the 1 to the right side, so negative 2z plus 1. In order to do that, I'm going to subtract. So my second step is subtract a negative 1 from both sides, after, of course, simplifying as we did. Okay, that's going to give me negative 2z is less than or equal to 3z, and that's minus 6 minus 1 is minus 7. Now I need to get all my z's on the left side. I can do that by subtracting 3x from both sides. So next, subtract, negative 3z, not x. We're working with z. Negative 2z minus 3z is negative 5z is less than or equal to negative 7. Looking at this, I have to then divide by negative 5 and reverse the inequality. Okay, so I'm dividing both sides by negative 5. As soon as I do that, I'm turning this into greater than or equal to negative 7 divided by negative 5. Finishing out up here, my negative 5's cancel out, so that's going to give me z is greater than or equal to, this is going to become positive, so greater than or equal to 7/5. Another way of writing that is z is greater than or equal to 1 2/5. So my solution set is that z is greater than or equal to 1 2/5. My first step was to remove the parentheses using the distributive property. I then combine the like terms to simplify. Use subtraction to get the numerical terms on the right. Use subtraction again to get the variables on the left. And finally, divided by a negative number to isolate the z, and that meant that I had to reverse the inequality symbol. And the solution set is z is greater than or equal to 1 2/5. So that one was a bit longer. And this one also has parentheses. So I'm going to start out by taking care of these parentheses. I'm going to multiply each term inside the parentheses by 3. So that's 3x minus 9. 3 times 3, so minus 9, plus 1 is greater than, I have to do the same thing over here on the right. 4 times x gives me 4x. 4 times 6 is 24, so plus 24 minus x. Before I go any farther, I combine like terms, which will give me 3x, and I have negative 9 plus 1, so that's negative 8. On the right side, I can combine 4x and negative x. So 4x minus x gives me 3x plus 24. So just by getting rid of the parentheses and combining terms, simplifying terms, I'm able to get a much easier inequality to work with. The next thing I'm going to do is subtract 3x from both sides. So subtract 3x from both sides. Okay. And that will give me 3x minus 8 minus 3x. To the right side, I do the same thing, 3x plus 24 minus 3x. Now, when I look at this, my variables disappear. They disappear. 3x minus 3x. X is gone. I'm left with negative 8. And on the right side, 3x minus 3x, again, the variables disappear. That gives me negative 8 is greater than 24. Well, negative 8 is never greater than 24. This is not true. If I end up with an inequality that is never true like this, my solution is the empty set. So it's the empty set. Again, most of the time you get a typical solution set which gives some restrictions on the value for x or whatever variable you're working with. But sometimes you end up with an inequality that is never true and gives you the empty set, or an inequality that is always true that tells you that this inequality is true, the solution set is all real numbers. So today we worked with some more complicated inequalities that required us to take multiple steps, including using the distributive property, using addition, subtraction, and multiplication and division techniques. See you soon on educator.com.